Yes, class. Am I audible to all of you? Amna, Deborah, Fadil. Where is Sidra? Sidra hasn't joined. Fine. So, class, in the last class, we had stopped at a point where we had derived the formula for force developed due to a single conductor, right? So, right now, we'll be seeing if two parallel wires are present. And here we are trying to find out the force between two parallel wires carrying current. Clear? Two parallel wires carrying current we are going to find out. So the formula for single conductor where we had stopped was force F is equal to BIL. This was the formula which we had seen, F is equal to BIL. Now, see, force between two long parallel current carrying wires, two long conductors with separation D. The separation between the wires which we have taken them as D. One current is I1, another current is I2. Both of them should be of the same length, which is L. L we have taken in this case. Now see, when we are finding out force on 2 due to 1, we should remember one thing firstly. When we are calculating force on 2 due to 1, force on second wire due to the first one. So see, if the force is being applied on the second, magnetic field would be produced of the first one, right? That would only be exerting the force. BIL formula, magnetic field is of the presence. So magnetic field 1 is not exerting on itself. If force is occurring on 2 due to 1, if only force was there, we would have directly used. But force on 2 due to 1 is mentioned. So due to 1 means you are clearly mentioning the force on second. So it is by something, that is by the magnetic field of the first one. So when we are saying magnetic field of the first one, what is the formula for magnetic field of a straight wire? It's mu naught I. Now for the first wire, we'll be using the current 1 also. So it is I1, 2 pi R, separation is D. So here we'll be using D. Now force on 2 due to 1, current is, or second one we'll take, length is same for both of them, but magnetic field 1 we will take. Sine 90 obviously is 0. Let me write it even. So this becomes I2L B1. So F21 is what? I2L B1 you will take from the first wire. That is mu naught I1 by 2 pi D. Now class, this is the equation. So what is the final formula we are obtaining? Final formula is mu naught I1 I2 L divided by 2 pi D. Mu naught I1 I2 divided by IL divided by 2 pi D. Now somehow class, see, this is the force between two conductors. This is the force between two conductors. Force between two conductors. Now see class, if somehow I bring this L, this length L, this is the main formula which you all should remember. If I bring this length L in the denominator, what will I be left with? Rest of the terms, mu naught I1, I2, L, right? All these terms I'll be left with. So when I say mu naught I1, I2, 2 pi D, this is what I'll be left with. So see, F21 by L is force per unit length, right? This is the force per unit length. So sometimes instead of using the above formula, we use this also, force per unit length also, mu naught I1, I2 by 2 pi D, right? And also force on, this was force on 1 due to 2, sorry, force on 2 due to 1. If you want to find out the reverse, just put a negative sign, values will be almost same. Fine, the values will be almost same. F21 is equal to negative of F1. Now regarding the direction, if you see currents are moving in the same direction of the wires, like if both the currents are moving upwards or both the currents are moving downwards in the same direction, upwards downwards is not of our concern. We are concerned with the same direction, whether upwards or downwards. So we say conductors will attract each other. If current is moving upwards, let's say, so they'll attract each other. So direction of motion for this wire will be towards this wire will be towards this. Even if they are moving downwards, this will be the direction. But if it is opposite, one downwards, one upwards, one upwards, one downwards, whichever wire, they'll repel each other. This is the direction which you have to use. No right hand thumb rule, nothing. Simple direction which is already mentioned in the question. That also you don't have to analyze by yourself. Clear? One more thing, then two things, then you people can write it. Definition of 1 ampere. See, definition of 1 ampere is what? Whenever a question comes to write the definition of 1 ampere, then you have to state current electricity. 1 ampere is the amount of current that is flowing per unit area. That one you have to define, and SI unit of it is 1 amperes and all. Class, if it specifically mentions you in the exam, if this specifically is mentioned to you to define 1 ampere in terms of magnetics, if it is there to define, then what will you do? See, force F21 is mu naught I1 I2 divided by 2 pi d. Fine. Both the wires are there, they are having the separation d, same thing, I1 I2 current, these are flowing. Fine. When we say to define 1 amperes of current, if you're defining, so you should put 1 amperes as well, right? I1 is equal to I2, which is 1 amperes. Fine. Okay. Separation also, this separation, let us take it to be unit, 1 meters. So I1 1 amperes, I2 1 amperes, separation D is 1 amperes. Now see what is left. F21 will be mu naught is 4 pi into 10 to the power minus 7. I1 is 1, I2 is 1 divided by 2 pi into 1. So this gives me 2. What am I left with? 2 into 10 to the power minus 7. So how will I define 1 ampere now? See, 1 amperes, this is the force per unit length, which is 2 into 10 to the power minus 7 when unit current flows separate through 2 wires separated through unit meters. I have already written this, you can read. 1 ampere is the current. See, 1 ampere is the current when flowing through 2 long conductors separated by 1 meters gives 2 into 10 to the power minus 7 Newton of force and can attract or repel each other. This is the general statement to define 1 ampere in terms of magnetics. Formula we will see. First you write down the entire theory portion for parallel wires, then we'll discuss it. Look at this question. You have to calculate force per unit length. So already per unit length is included, right? So length is not needed. So we'll be using the formula mu naught I1 I2. F21 will be mu naught I1 I2 divided by 2 pi d. So this is 4 pi. This is 4 pi into 10 to the power minus 7. This is 2 into 10 divided by 2 pi into 2. 2 will be cancelled. This becomes 2. That gives you 20. No, 2 into 10 to the power minus 6. Newton. Now direction. So both are in the same direction. So they'll be towards each other. So when you are calculating force per unit length on conductor 2, so in which direction is conductor 2 moving? Towards negative x-axis minus I cap. Fine. Similarly, when this is for the first part, when you are calculating for the second part, F12, that is minus 2 into 10 to the power minus 6. This is moving towards the right. That is I cap 1. This is how you have to answer. Write down this one more question we'll see based on this topic. See the second question. Here a rectangular coil is given and a straight wire is given. Let us name this something A, B, C, D. So now we'll divide it into sides and solve. Now see AB, BC, CD and DA. These are 4 straight wires given to you which you have to solve. When we are talking about the sides BC and AD, see here the direction, when we are calculating the direction of force, see this will be attracting it, right? Both the direction are in the same. This force, this is FAB. When I talk about CD, this is in downward direction, this is in upwards direction. So both of them will be repelling each other. So this will be the direction. Similarly, this will be upwards, this will be downwards, they'll cancel. This is of no need to us. We just need FAB and FAD. So how will we write it? See, the net force will be, we'll not use the formula force per unit length because force is asked to us. So this becomes mu naught for this wire and this wire I'm writing. Okay, mu naught I1 because I1 current is flowing in this coil. I2 length of this part is B. See, it's given. B divided by 2 pi, separation is D. What is the direction? Negative x-axis minus I cap. Fine. Plus, talk about this wire CD and this wire C. Mu naught current I1, second current of this wire I2. Length is B divided by 2 pi. Yes, Fadil. After 2 pi, what should come? D.
D plus L, ma'am.
Perfect. D plus L. Because this separation is L. So this becomes D plus L. All
Yes,
right.
ma'am.
Correct. Perfect. Sidra, what should be the direction? I should write. Again, minus I cap only should I write or something else? Sidra. I have already drawn the direction, so you just have to read it out. Amna, direction. See, for this, I have already told you minus I cap here. I'm asking for this wire, CD. Fadil, correct? Amna or Sidra? Yes. Sidra, I think you unmuted yourself.
I cap.
I cap. Perfect. It's I cap. See, this is the direction. So it would be I cap. And this is your answer, this much of newtons. Now, if values are given to you, substitute the values, you have your answer. Fine? Write it down. A very small topic is there, magnetic dipole. I just briefly, I want to tell you before we start with torque. Now we actually have to start with torque. So to start with torque, one topic I have to discuss. Today we'll complete this lesson, don't worry. Write it down first.
Ma'am,
Yes, Fadil.
ma'am, what about FBC and FAD?
See, these
Force
forces
on.
will cancel each other, no?
Yeah, but I didn't get how force BC is like upwards.
See, this is like, this is one wire. This is the wire you
Hmm.
are considering. Now you apply a right hand thumb rule. You keep the direction, right? Along the,
Hmm.
you keep the direction of the current of your hand along the direction of current. Fine.
Right.
You will curl your fingers towards the wire second. Now what will happen when you are curling your fingers towards the wire second? The thumb is pointing up.
Force is upwards, right? Okay.
And similarly, it would be downwards for it.
Right, right. Okay.
Okay. See, the next topic that I wanted to tell you was current carrying coil as magnetic dipole. Now see, torque we have to do. So we'll do magnetic dipole separately in chapter 5 tomorrow. When we'll start, we'll do this topic separately. But before that, you should just have a brief idea so that when we are discussing torque, because magnetic dipole moment will come and the formula will also be used. See, one thing remember when we are talking about the direction. So best way is that when you have to identify the direction of the coil, if you know the polarity, you can easily answer it. See, when I have south polarity, on one hand, I have north polarity. Just at the tips, mark the arrow. Which direction is this? Can you see? This is clockwise. Fine. See, this is anti-clockwise. Like this, you can remember the direction. Now, when we are talking about magnetic dipole is formula is N number of turns into current into area. No derivation for it. Just remember the formula. This is magnetic dipole. See, N is the number of turns. I is the current. A is the area of the coil. So direction is curl your fingers along the sense of current. Thumb gives the direction of magnetic moment. Like see these two questions. This first question here, a circle has been made. A circular coil is present. 2 amperes of current is flowing. 1 meters is the radius of it. Number of turns, this is 100. Fine. So magnetic moment, when I say formula is NIA. Number of turns 100. Current is 2. Area pi r square. What is the radius? Radius is 1 meter. So 1 square pi r square. This becomes 200 pi ampere meter square. Now complete answer would be 200 pi. Curl your fingers, take your right hand, curl your fingers along the direction of current. Current is going like this. Yes, clockwise, this is how the current is flowing. Clockwise direction. So when we curl our fingers also, direction of magnetic moment will be in this direction. Curling it. So thumb is pointing inwards, minus k cap, negative z axis. Fine, negative z axis. So minus k cap, ampere meter square, because current into area. The actual formula is current into area only, no? Number of turns is being just multiplied for the number of turns that are being added, right? For one single turn, the actual formula is current into area. That's why we are writing it as IA. Secondly, this is a square which is given, same thing, M is equal to NIA. This is more simple. This is simpler than the previous one. 100 into 2 into area, length into breadth. Simply 800. Now this is moving like this, right? So this is the direction. Curl it. Thumb is pointing outwards, away from the screen. So this becomes K cap, ampere meters. This was what I wanted to discuss. Then we'll start with torque. Write it down first. Fadil, direction you didn't understand. See, you have to curl your fingers along the sense of current. In the first part, current is moving like this, clockwise. Curl your fingers clockwise. Thumb is pointing inwards. This is how no, you will curl clockwise. Look. This is the direction clockwise. Anti-clockwise, look. Fingers are going anti-clockwise. So this is it. Now clear or not, Fadil?
Okay, ma'am.
Clear?
Yeah.
Okay, torque, let us discuss. Torque is a very small topic because again, these things have to be dealt again. Torque's very small derivation is there. Just understand the basic what all things are occurring. So this is it. A, B, C, D. A coil is there. Rectangular coil is there. Length L, breadth B. Fine. So here, current that is moving is I in the coil. One more thing. Magnetic field is there. B is the magnetic field lines. And the angle that the magnetic field line and the plane is making is theta. The plane of the coil and magnetic field is making is theta. Now see, when we are talking about the forces for the AB segment, you have to keep your current along the direction. You have to keep your right hand along the direction of the current, right? Then you have to curl it towards magnetic field. Thumb is pointing upwards, the way Fadil was asking for the previous question also. So here force will be upwards. This is FAB. Similarly, for AD it is like this, curling it. This is kept for AD, curling towards magnetic field. Force is like this. See, this is B, forces outwards for it. So for outwards, it would look like this, FAD. B, see CD, like this. Curl it outwards. So this is like this. Outwards you can say, or downwards you can say CD. Then this magnetic field, no, magnetic field is here. So this will be FPC. Fine. Now see, we'll be applying F is equal to IL cross P. This formula we'll be applying. So F will be ILB sine theta. Magnetic field line and the plane is already perpendicular. So I'm writing it directly as ILB. Now see class, if you notice the net force is actually 0. If you look here, ILB is the magnitude for all. But for upwards, it was J cap. Then it became ILB minus J cap for the CD, AB, CD. Yes, CD1, right? Minus J cap for them. Minus J cap. Then for BC, it was negative x-axis minus I cap. ILB minus I cap. For last one, it was ILB, which was moving away, plus I cap. They are cancelling each other. F net is equal to 0. Why are we mentioning this? We were calculating torque. Whenever you are calculating torque, before that you should remember, see torque's derivation, we'll do it separately, but you should remember that net force is also 0. Why? This will give you a hint that translational equilibrium exists. If this is not occurring, translational equilibrium is not present. For torque, just remember formula of torque is M, which you have just studied, magnetic moment, M cross B. This is a formula which you have to remember for torque, M cross B. Fine. Cross product, so what should come, sine theta or cos theta?
Sine theta, ma'am.
Perfect. This is MB sine theta. M also we have written NAIB. This was also one formula with sine theta. Fine. If just in case your sine theta, sine 90 is present, you can equate it to 1. Fine. When your theta is 90 degree, so torque will be the greatest, that is NAIB. Why are we discussing torque so urgently? If we have to do it again, we have to discuss it. Why are we doing it so urgently? Because the next topic or the last topic that we'll see, conversion of galvanometer, there the concept of torque will be used a bit. Write this down. Last topic we'll start. We'll be able to finish it. Tomorrow we'll start with chapter 5. Translational equilibrium means, see, one is rotational equilibrium. When the rotational component is not existing, means rotationally all the torque is zero. Translationally in equilibrium means body is not moving in a straight line. Body is static. That is what is meant by translational equilibrium. Yes, class. Now conversion of galvanometer into voltmeter and ammeter. But before that, you should understand what is the meaning of galvanometer. Galvanometer is basically a device which is used to detect current in your circuit. All right. In moving coil galvanometer does not tell you the amount of current in your circuit. It does not tell you anything related to voltage. It just tells you whether yes or no there is current present in your circuit. Now, principle, we'll see it later. First, see the construction. Construction is simple. See, two permanent magnets are present. Two permanent bar magnets are present. These two. They are permanent bar magnets. All right, these are permanent bar magnets which are present. They are carved, radially carved, so that radial magnetic fields are present. The magnetic fields which are arising, these are radial magnetic fields which are arising. So these are basically radial magnetic fields. Also, they are uniform. These are uniform. Don't think that if they are radial, they are non-uniform. Uniformity is not depending upon the geometry they are forming. All right. So these magnets are present. They are carved on one hand, then on one side, and other hand is free. They are just attached. Then a soft iron core. The circular part, can you see? This is basically a soft iron core on which copper windings or any wire is wrapped like this. All right. And then at the center, this spring is attached. This is a spring. This you see, no, this is a spring. Spring is attached to which at one end pointer is there. This is the scale. This is what is visible to us. When we see a galvanometer, you must have done your practicals in your school. You must have seen a galvanometer. You just see the readings and the pointer moving. So actually, this part is only visible to us. The other mechanism is hidden behind. So this is the scale. And this is the pointer. Now what happens? Torque comes into action. See, basically there's a deflecting torque. Deflecting torque means the torque which you have just studied, the torque that will come into action because of presence of magnetic field. That is NAIB. You must have done SHM and waves in your class 11th. F is equal to minus KX is the condition for SHM to be obeyed. Then we have torque also, that is minus K theta. This is also condition to be obeyed if you have to follow SHM. All right, simple harmonic motion. So this you must have done it. So whether we're talking about SHM or not, restoration will always occur. If the deflecting torque is rotating, one anti-deflecting torque is present to rotate it back. Deflection is occurring, then deflection is coming back. So which is making it come back? That is the restoring torque. Force will not come into action because pointer is rotating actually. This is rotation of the pointer which is visible to us on the screen, which is equal to K theta. Now come to the principle of it which we have left. If a current carrying coil is placed in a magnetic field, then it experiences a current dependent torque, which I have told you, that tends to rotate it and produces angular deflection. Current carrying coil is placed in magnetic field. Current carrying coil means your wire that we have kept. Fine. Because of magnetic field, torque came into action, and torque is a rotational force. So it rotated the pointer. That's why we had it in our system. That was the principle which was mentioned. Now you just have to equate both of these. NAIB is equal to K theta. So basically deflection, last line was produces angular deflection, right? So angular deflection, this is NAIB divided by K. K is what? See, theta is angular deflection. This is angular deflection. K is torsion constant. K is torsion constant. Basically, these K constant, these are known as spring factor. For different systems that we have in nature, different types of these are present. Fine, spring factors values are present. Like if I say pendulum mass system, so value of K spring factor becomes spring value is 2 pi, right? You must have heard of the formula T is equal to 2 pi under root L pi G. So that is something else. When we are talking about spring mass system, the spring factor becomes spring constant. So different values are there for different systems. Now, one topic is sensitivity of galvanometer. In normal term also, when do we use the word sensitive? In your normal literature, English literature, what do we use? When do we use the term sensitive? If I say a person is very sensitive, it means even the matter that is not very serious, not very highly intense, a small change is observed in the person, right? A very small change is even observed in the person. For a huge reaction, for a huge stimulus, huge reactions are expected, right? For huge stimulus, huge reactions are expected. But if the stimulus is very small and huge reaction the person is giving, so what we say, the person is very sensitive. This was not a matter of discussion. It was a very small thing, right? So similarly, just relate it with galvanometer. For a very small amount of current, huge deflection galvanometer is showing. So we'll say galvanometer is also very sensitive. Fine. Now, this way, this is just for understanding. For calculation purpose, for current, we have current sensitivity and we have voltage sensitivity. Sensitivities are divided into two parts. So deflection per unit current is known as current sensitivity, and similarly here also deflection per unit voltage is voltage sensitivity. Now what we have derived for theta, NAIB by KI. So current will be cancelled. This is NAB by K. This is the form. Come to voltage sensitivity. This is theta. Voltage is according to Ohm's law IR, right? So see, what is theta by I? Can you see theta by I is actually current sensitivity? Current sensitivity is NAB by K and this R. Understood? This is theta by I. This is current sensitivity, which is NAB by K. So NAB by K, this R. All right. Write it till here. Tomorrow we'll continue class. Just a small portion is left. So this lesson is over. And tomorrow we'll start with chapter 5. There's a small portion, conversion, that we'll do tomorrow. Okay, class, let's meet tomorrow. Thank you.
Thank you, ma'am.